Hello and welcome. I will teach you the basic rules of Boolean algebra. So I have drawn this circuit over here, which isn't an ordinary circuit but a logic circuit. So I have several gates and I have three input signals. I have the signal A, signal B and signal C, and the output signal X. The input signals are also called domains, and all these four signals will be treated as variables in our equation. So in order to write this as an equation, we'll first need to translate these gates or operators to math language. So and will be represented by a multiplication sign or a product, while the OR gate will be represented by a plus sign. So to write it as an equation, we'll first AND A with B and then AND with C. Now the output here is then ORed with A, which is exactly the same signal as we used over here. And this whole thing will then be ANDed with A. And finally we OR this whole thing again with the input signal C. And this produces the output signal X. So the variables in this can be one of two values. They can either be a logical high or logical low. This is of course important to note since it'll be really useful when I'm teaching you the laws in a minute. So why do we learn those laws, and why do you need to learn some basic rules? Well, if you look at this expression, it's quite complicated, and it's actually possible to simplify or reduce this to only contain one gate, and it looks like this. A ORed with C equals output signal X, and this is obviously way easier to build in real life than this complicated mess. So let's get to the laws. So the laws I'm going to teach you are quite important when you want to simplify or reduce an equation. However, it's more important to understand the logic behind them than to remember their names or remember how you write them, since that is what you'll be using when you're reducing or simplifying. So let's get started. So the law of identity is quite simple. Just A equals A, and A complementary of course equals A complementary. Nothing new or surprising here. So the next is the double negative law, which just says that if you have A, it equals its own complementary if it's complementary twice. And those complementary values can of course be stacked as long as they come in pairs. So it could be 4 complementaries, or 6 or 100, or really whatever, or as long as they come in pair of 2s. Next is the law of union, which goes like this. If you have A and OR it with 1, you will get 1. And it doesn't matter if A is 0 or 1, since in an OR gate you only need one high to output a high. However, if you OR A with a 0, A will determine what the output is, since 0 obviously doesn't give a high output. The law of intersection is like the one above. However, we use AND gates instead. So we have A ANDed with 0, which gives whatever the value. No, actually it always gives 0, while A ANDed with 1 always gives A. And this is because when you use AND gates, you always need 2 highs to output a high value, and if we have a 0, we are already missing out of 1 high, and we need both of those to output high. And here of course we already have a high. However, A also needs to be high to output a high. So if A is low, we will return or output a low. The idempotent law looks like this. If we have A ANDed with A, we will always get the value A. And same goes for OR gates. If we have A ORed with A, we will always get the value, the output value A. Next is the complementary law, which looks like this. A ANDed with its complementary value is always 0, since one of these has to be low, and you can't have a low in an AND gate if you want high output. So 1 ANDed with 0 or 0 ANDed with 1 will always give 0 or low. However, if we use an OR gate, really the opposite happens. Since we always have a 1, we always output a 1. Next is the distributive law. The distributive law is really just factorizing. So if we have A ANDed with B ORed with C, we get A B ORed with A ANDed with C. So what we do is really simple. We just multiply A into the parentheses. Next is the law of absorption, which goes like this: A ORed with A ANDed with B equals A. This can be shown by using this law, distributive law, from above. So what we have is we have A ANDed with 1 plus AB. And this can be written as a parenthesis, where we have A on the outside and we have 1 plus, ORed with B on the inside. And we already know what 1 ORed with B is. It's always high, so we have 1 ANDed with A, and that's of course A. So finally we have the law of common identities, which is written much like the one above. However, this time we A OR with complementary A ANDed with B, and this equals A ORed with B. However, to prove this, we also use the distributive law, but we also use some of the other laws from above. So by having them in mind, we start by writing A as we did in law of absorption. So we put A as A ORed with AB, and we remember that AA also equals A. So A ANDed with A is put here, and then we put a 0. We can OR with as many zeros as we want. So we OR with 0 called A. So we actually OR here. So A ANDed with A complementary, and then we OR with our final value from up here. So we OR with A complementary B. And this of course equals A ORed with B as above. Now we can probably already see that this is easily factorized to A ORed with A complementary, which is ANDed with A ORed with B. And this equals A ORed with B. So what we really have is just A ORed with A complementary, which we know is equal to 1 or high, and we AND that with A ORed with B. Yeah, and that's of course A ORed with B. I really recommend that you try to look at these laws by yourself and think, okay, why does this rule make sense? Like not look at, don't look at the proof, but look at the law itself and try to understand what makes this possible just off the bat without looking at the mathematics below. And I think that's probably the most important part of learning these laws, you know, trying to understand why they work instead of looking at how we prove that they work. So let's look at the original, or the equation that I made at the beginning of the video, and try to simplify it. So you can probably already see that this is quite a simple example. So we'll drag this down here, and all right. So what we have is we have a parenthesis here, and inside we have A ended with B ended with C, ordered with A. And as you learned in, I think, the absorption rule, we know that this equals A, which is then ended with A again, which is ordered with C. And as you know, A ended with A is, of course, and most definitely A. And this is then ordered with C. And we have the output X. So as I said, it's a really simple example. But just by learning those laws down here, you can take on way more complicated circuits than this, and find an equation which is much simpler, much more simple than the one you found original by just analyzing this. However, as they get more complicated, you will also need to learn De Morgan's laws, and I'll be walking you through these in another video, which will also be about how we switch gates instead of just reducing. So maybe you want to make an equation of only OR gates or only AND gates, or maybe even only NAND gate, which is quite fun. So yeah, and that's it. Thanks for watching.